In this module, we touch the basics of particle acceleration and detection methods. In this video, we'll continue our discussion of particle detection techniques with semiconductor devices. After having watched this video, you will know how semiconductor detectors detect the ionization caused by traversing charged particles and how this is used to identify charged particles and to measure their trajectories. This particular type of ionization detectors uses the properties of semiconductors to detect and measure the E by the X of charged particles. When a charged particle traverses a semiconductor, it will create an electron-hole pair. Since the conduction band is close to the valence band, it takes only 3 electron volts of the E by the X to create a pair, compared to the 30 electron volts to ionize a gas atom. The charges can be detected by applying an electric field. Semiconductor detectors have very good energy resolution. They are compact since they are made of a solid. They are thin with a required thickness much smaller than the radiation length. The spatial resolution is of the order of the micrometers, ideal for tracking detectors. And they also produce fast signals. However, they are expensive, they are fragile to mechanical, chemical and electrical impacts, and their performance is degraded by irradiation. The basis of a semiconductor detector is a PN junction with reverse bias. When two different semiconductor types, N and P, are in contact, diffusion creates a zone free of charge carriers around the contact surface. A depletion zone forms at the junction, creating a potential barrier, which prevents conduction between the two semiconductors. The application of a reverse bias voltage widens the depletion zone, and this is how semiconductor diodes work. The passage of ionizing particles liberates electron-hole pairs in the depletion zone. Charges are collected to both ends, and the diode conducts a small current for a short time. Semiconductor detectors have a good efficiency since only 3 electron volts are necessary to create a single electron-hole pair. So these detectors are 10 times more sensitive than a gas and 100 times more sensitive than a scintillator. It therefore has a lower detection threshold and a better energy resolution, since more primary ionization means less signal fluctuations. The threshold for the E by the X is very low, so there is a good linearity. However, to measure highly ionizing particles requires a large dynamic range of the readout electronics, since the E by the X is proportional to the square of the charge of the particle. Even if the junction is in reverse bias, there is still a small current of the order of the nanoamperes through the junction. This is called leakage current, and it is due to the motion of minority carriers, effects of impurity, and surface effects. The time of the electrical signal is of the order of nanoseconds, so semiconductor detectors are as fast as scintillators, which we will discuss in the next video. The energy deposition by the E in the X is very local. Therefore, the electrodes can be structured on one or both sides to locate the passage of particles. The distance of metallized structures, called strips, is typically of the order of 50 micrometers. And in this picture you see example of silicon microstrip sensor of the AMS detector, which is operating on the International Space Station, and of the ALICE detector operating at the Large Hadron Collider. Each channel of the metallic structure must be connected to the readout electronics through microbonding. Application of semiconductor detectors in particle physics include the following. They are used arranged in layers to measure the trajectory of charged particles, and this profit from the development in microelectronic technology to fabricate precise structures on silicon and other semiconductor materials. Examples are microstrip detectors used in ATLAS at the Large Hadron Collider and in AMS, pixel detectors, which have been used for the first time at LHC, charge-coupled devices, CCD, used in digital cameras, and many others. Semiconductor detectors also measure the deposited energy. The excellent resolution allows the identification of the charge of the penetrating particle in a tracking device. They can also be sensitive elements in a calorimeter. Their application is only limited by the thickness of the depletion zone, which goes from 50 micrometers up to order of millimeters, and the maximum chip size that can be produced, which is about 50 centimeters squares. Here is an example of a silicon wafer, so the big rectangle at the center, and at the sides there are testing circuits which allow to test the quality of the sensor before using it to assemble a detecting unit. So before using it, one must cut the sensor, and this is an example of a cut sensor. And usually one connects several sensors together to build a detection unit like this one, where there are two silicon sensors connected at the middle by microbonding, and then at the one end microbonding connects them to the readout electronics. So more example of application of use of semiconductor sensor will be shown in video 3.10. In the next video, we'll first talk about scintillators and Cherenkov detectors.